Next, we will look into pericyclic reactions. A pericyclic reaction is one that happens without ions or free radical intermediates. There's three types of pericyclic reactions. There's the cycloaddition. We have a diene here and an alkene that combine together. This 4-carbon chain here is from the butadiene. This is from ethene, so you can see that carbon there. If I follow where the electron's going, I have this pi bond goes here to form a new bond. These pi electrons go here to form a double bond. These pi electrons went here to form a new bond. So now I've made cyclohexene. You can have electrocyclic reactions where the electrons move within a system to form a ring. So these are the carbons that were there. Then I follow my electrons. These ones right here, A goes to form a new bond. B is going to form a double bond in a different spot, and then C also goes to form a double bond in a different spot. So now we have this closed ring system. The third type is a sigmatropic rearrangement. It's similar to the last one where we saw electrons moving around in a system. Here we create a new sigma bond without destroying any sigma bonds. In the sigmatropic, we're going to destroy a sigma bond. So here we have created one sigma bond. In this one here, if I look at my electrons, I'm just going to draw these. I'm forming a new sigma bond here. This one forms a new pi bond. I'm breaking this bond right here. We get a pi bond there, and that is our product. So in the sigmatropic rearrangement, we are making a sigma bond. So one sigma bond is broken. These reaction mechanisms are concerted, so they don't have any intermediates. All of the electrons are moving at one time. The reaction mechanism involves a ring of electrons moving around a closed loop. And the transition state is cyclic. These are characteristics of pericyclic reactions. So in a cycloaddition, the number of sigma bonds that are changing we are forming 2 sigma bonds. We are losing 2 pi bonds. In the electrocyclic reaction, it is +1 and -1. And in the sigmatropic, we're not changing sigma bonds or pi bonds. So the net number is the same, even though we're making 1 sigma and breaking 1 sigma bond. The net effect is 0. The Diels-Alder is one of these cycloaddition reactions which are very useful. You start with a diene and an alkene, which can also be called a dienophile because it loves the diene. And what happens in this reaction is a concerted reaction, which means all these arrows are moving at the same time. These pi electrons go here to form a new sigma bond. These pi electrons go to form a new pi bond, and these ones form a new sigma bond. This is the new sigma bond, new sigma, new pi. Again, we have cyclohexene. We have cyclohexene. If we look at the potential energy of how this works, these two groups by themselves have this level of energy. It has to overcome a great amount of energy in order to form this pericyclic reaction. And then there is the product down below. So we very quickly made a cyclic system from butadiene and an ethene. And this group of gentlemen, Diels and Alder, won the 1950 Nobel Prize for this reaction. Most Diels-Alder reactions are thermodynamically favored at low and moderate temperatures. So we want to do this at low temps. So you can see which bonds here are being broken. We have 3 pi bonds being broken, and then 1 pi bond and 2 sigma bonds that are being formed. If you cook up these reactions too much, such as over 200 degrees Celsius, what we can see happening is the product would form and then it would revert back. This is what we called a retro Diels-Alder. That is 200 degrees Celsius. This reaction involves the diene and the dienophile, or alkene. If you do this reaction at 200 degrees, this only happens in 20% yield. If the dienophile is not substituted with an electron withdrawing group, it is not favored. If you heat it up too much to try to get the reaction to occur, it will result in the retro Diels-Alder. If you want the reaction to proceed smoothly, we want to put an electron withdrawing group on the dienophile. So this is our electron withdrawing group. So when you have this on here, the reaction will just go. It's spontaneous. So we form the cyclohexene, and the electron withdrawing group is still there. So this reaction is spontaneous. These are other electron withdrawing groups. So any of these on the dienophile will help the reaction to proceed very smoothly. Diels-Alder reactions are stereospecific, depending on whether an E or Z dienophile is used. If you do this reaction with this Z alkene, these attack from the same side. This is the new alkene that's formed. Your halogens will be on the same face as each other, so they won't switch to trans all of a sudden. In this reaction, it's going to be the same thing. If you had the E alkene, you'll have one up and one down, plus you would also get the enantiomer. So if you started with the Z, you get a cis. If you start with E, you get trans. We can also use an alkyne as a dienophile. The reaction mechanism is exactly the same. We took one of these electrons to form a new sigma bond. This forms a pi bond, and then we get another sigma bond, and this alkene is left. So we end up with a cyclohexadiene. You can attempt a couple of different reactions here. You want to make sure that your reagents are lined up properly. So it makes more sense to draw it next to it where we can see the diene. Okay, so I have methyl groups on the alkene, and then this group coming off of there. When I'm making this new bond, this is the new bond that is forming. We're going to push that one up out of the way. Then I have 2 methyl groups here, and I'm going to approach this from the bottom side. So this will be a dashed line. This will be dashed. That methyl group got pushed up. I still have the methyl group over here, and there's a new pi bond that was formed. Okay, so in the next problem, we're looking at a retro Diels-Alder, where we have to draw the product backwards. This is the electron withdrawing group. So my Dienophile came from here, and I have a cyclohexadiene. Which tells me I probably have a triple bond before then. So if I draw my electrons now, these probably went here, this goes here, that goes there. So the electron flow is the same, but we're now breaking a sigma bond. So I have the Cn, double bond here, here, and then that is the triple bond. And then to look at this Diels-Alder, this is my diene, this is my dienophile. Electron movement is the same. So all of these just come along for the ride. I will still form cyclohexene. Diels-Alder can be affected by diene structure. If you recall from the beginning of the chapter, we had S-cis and S-trans conformations. If you have the S-trans, we have no reaction. In the S-cis, we do see a reaction. If your diene is part of a ring system, the bridgehead, so this carbon right here, gets bumped up. So I'm going to draw that up here. This is the new bond that is formed. Then you have the cyclohexene that was formed. And then there is this ring that was from there. So the double bond. So the electron movement is the same. This is the product that you're going to get. It is a little bit tricky to see, but this carbon here that's up is this guy right here. So Diels-Alder cannot react with the S-trans. C1 and C4 are too far apart. Cyclopentadiene is so reactive here that at room temperature the 2 molecules will react together. Diels-Alders can also have endo preferences, and that is just talking about how the dienophile is approaching, and it tends to do so from the endo position. If I draw my electrons here, okay, so the way that I'm going to draw this is a little bit different than you're used to seeing. There's that. This is the new bond that was created. And this is the bridgehead. That's the new alkene. The CHO groups, or these aldehydes here, are sticking down. This is the endo major product. The other product that could theoretically form is the exo. Bridgehead is still up here. But now the aldehydes are sticking up. This is the exo product. This is minor. That's the exo minor product. So when bicyclic systems form, the endo and exo are used to describe where the functional group is positioned. So this bridge has 1 carbon atom. This bridge here, this is considered a bridge, has 2 carbon atoms. That's the larger bridge. The endo product has the groups that are syn to the larger bridge. This one is exo, this is anti to the bigger bridge. So the endo product has the groups on the same side as the larger bridge. This is highly favored. So the mechanism you can look at here, there's a favorable interaction with the electron withdrawing substituents to form this endo product. And here, the aldehydes are too far apart to contribute their electron withdrawing capabilities, and so this is the less favored.